Oh, I didn't plug this in. Duh. Alrighty then. So, for review, you said statically indeterminate. Wait, no, composite. I don't know.
I think the four of us should pass.
I think we should all get hundreds before the test because we can.
If nobody else comes up, I'll give you guys 5 bonus points for the exam.
Really?
Yeah.
I have no one.
Double and give two times.
Double it and give us the next person.
All right. It's gonna go, I'll say plus 10, and for every other person that comes in here, it's gonna be minus 2. So if Edgar comes in late, you guys get plus 8 points now. If Asa comes in and Edgar, it's gonna be plus 6. It's gonna keep going down.
Okay.
All right.
I'll stand at the door and be like, there's
And then once enough students come in, then it'll be like, I don't know, how many students are still missing? That's like 4?
Because 1, 2, 3, 4.
4,
The
yeah.
rest don't come.
All right, so then I have to do. I'll give you guys plus 5 then, and subtract 2 for every student that comes in.
oh, we're gonna get
So that-
points all for itself.
Yeah, for students being late. All right, let's say box here. With then just a rod. This is an atrocious figure. This is why I didn't become an architect. Oh my god. I have no artistic talent. There we go. And then for this, I'm gonna do an inside material here. And then one more material there. It's material 1. Nope. Material 2, and then material 3. So this core here will say, I don't know. Oh yeah, I have everyone's homeworks, by the way, so I will hand those back once. Yeah. All right, so we'll say that this red core is about a 1/2 inch diameter A36 steel. The blue is about 1 inch outside diameter. I don't know. Let's say gray cast iron. And then it's of course 1/2 inch internal diameter. And then this outside core here, not that it's a core, but we'll make this aluminum? Yeah. And we'll make this 1.5 inches with an ID of about 1 inch. All right. Now the length of the rod, not that you need it, we'll say is about 12 inches. And then we'll say that this torque here is 2 kip feet. All right, I'll give you guys a few minutes just to determine the internal force. Actually, scratch that. I don't want to give you guys the force. I'm going to make it a question mark. And if the angle of rotation is 1.5 degrees, then what does the torque have to be? There we go. Just made a way to make this problem more fun. Everyone did pretty well. So I think everyone's ready for their exams. Uh-oh, everyone's bonus points just went down too. And another 2.
Tommy, no! Why did you come in here? We just lost 4 bonus points because of you.
No, I think everyone's still got 2.
Oh,
Yeah, so if Edgar comes in, everybody's bonus points goes. Yeah. Wait. Oh, wrong one. This is the one I want to do. My bad. Kidding.
Can I get the bonus points since I didn't show up? Is that part of the deal?
Everyone's supposed to show up. So they were saying like that they wanted 10 bonus points since only 4 of them showed up. But then we negotiated it down to about 6. But it's contingent, so you lose 2 points for every person that walks through that door afterwards. So you just cost them 4 points. Oh, there goes the rest of your bonus points. If Edgar walks through those doors next, everyone's losing 2 points on the exam. Yeah.
To find a J of the alloy,
What?
to find J for the alloy, do you just take the OD to the and subtract it from the ID? Like find
It's
the radius of them?
Outside minus inside, yeah.
Okay.
Yeah, whenever you're finding J for like outer shapes, outside minus inside. refrigerator in there. And -2.
That's a joke, I don't know. Not taking anyone.
Yeah.
Can you check?
What?
Can you see if I did this right?
All right, let's see. Delta C, delta C, J is 125 to the fourth, 0.5 minus 0.5, and then 0.75 minus 0.5, okay. Your procedure looks right.
Did you say most likely incorrect?
It's like 0 to 6, yeah.
Is it normal to be small? That's not even possible.
Well, you need to remember, the outer part is going to be carrying a lot of torque because it has a much larger moment. So because of that, I would actually see that occurring. The only time I don't think there would be a lot of torque is if there would probably be more torque if you had a less stiff material in the center. We'll work it out, but that looks good. All right, give you guys a few more minutes. Other than Mike, who's got it? Oh, did I see her hand raised? I thought you raised your hand. What did you get? Yeah, probably. I'm getting too close to the exam date for me. In here. Oh, you're drawing it out?
Oh, sorry, no.
I was making a snowman.
Oh, I thought that was the next one.
Kidding.
You just hold them all.
Did everyone solve the first problem?
Olivia, I think you got it, right? Solved it? You don't know? You got 4, 2. 4.2, 2.030. Okay, that is entirely different than what Mike got. So somebody made it. Who here has answers they want to submit? Emily, I'm looking at you. Did you solve it? Where are we at? What was your total torque that you got?
4.2.
For everything?
Wait, what did you get?
4.04?
No.
Oh no, that aligns with what Mike got.
I got 4.610.
With some round off error, yeah.
Why?
You got 8.46. Okay, that's one submission. Mike's laughing at you, by the way.
Well, I
No,
didn't
no.
want to submit it, it was forced to.
Fourth submission. All right, let's go over this together. All right. First, we need the J values for everything. So, J for the steel, J for the cast iron, and J for the aluminum. For the steel, pi over 2 times 1/4 of an inch to the 4th. For the cast iron, it's going to be 0.5 to the 4th minus 0.25 to the 4th. And then for the aluminum, 0.75 to the 4th minus 0.5 to the 4th. Did everyone get that? What did you get for it, Mike?
Which one?
All of them.
I got, for ST, I got 0.006. For GI, this is what I got 0.09. And then for the aluminum, I got 0.40.
What did you get? 0.48?
0.40.
0.40. Just Olivia, is this what you got for the J values for everything? Give or take? Awesome. All right. Now, the G values. GST, GCI, and GAL. We just look on the tables. For A36 steel, it's going to be 11,200 KSI. For the cast iron, it's 4,100 KSI. And then for the aluminum, we said 6061, so it's 3,700. Lastly, we know that the length for all of the materials is consistent, so it has to be 12 inches. And then from there, we could just calculate the torque in each material. All right, we know that phi is equal to TL over GJ. We can rewrite this to say T is equal to phi GJ divided by L. One problem that you guys should hopefully know by now is our angle needs to be in radians. So what you need to do is multiply that by pi over 180 to convert it to radians. Let me just grab my calculator really quickly just so I can do like some sanity checks here and there, but I'm fully trusting you guys. What did you get for the angle?
For which one?
In radians, yeah.
Oh, 0.026. Radians.
Exactly. And so we take that value and we just plug it above. So we're going to have a torque for the steel, a torque for the cast iron, and a torque for the aluminum. 0.026 radians times 11,200 KSI times 0.006 inches to the fourth, all divided by the length, which we said was 12 inches. And then you just repeat this process of just writing the values down for the other materials. And then 0.026 radians times 3,700 KSI times 0.40 inches to the fourth divided by 12 inches. Who got up to this point? This is the majority of the problem. It's just doing this. Awesome. What did we get for the torques, Nicole? All right. And then the last part of this problem, the sum of those torques is equal to the total torque that was applied. What was the sum of that, Mike?
I got 4.16.
4 point what?
1.6.
0.6.
I just rounded it up. 1.6.
Yeah. 1.6.
Mine was just rounded up.
All right. As long as your procedure was right, there could be some round off error in the number that'll make the number fluctuate between probably like plus or minus a quarter of a kip inch. You know, it's not going to be a big of a deal. So as long as your procedure followed this, like I know your number was slightly different, right, Olivia? Than, yeah. So, some slight round off error. All right. Problem 2. I want you guys to determine the rotation in each of the rods, EF, CD, and AB. I'll give you guys about 10 minutes. I should put a timer on. Yep, you guys got 10 minutes to solve this problem. go. And then five minutes. If this is my exam on Monday, I have 10 seconds left to stay on track. Yeah,
What is that sin set of 1 inch? Oh, never mind. This is typical.
to the 4. That's J. Yes.
I saw you do it, but what if, so when I did the tools, these would be the same because they're the same grades.
Well, you calculated the force that's transferred, which would technically be the same as these brought here.
But I did, I saw that I had two equals, two divided by 1 equals.
So it's going to be
It'll be for both. And you don't have to multiply this by 80 next time, since it wasn't
If you, as long as you're at the units, you could display your units in degrees, just make sure you always do the calculations. So.
Yeah, because I didn't multiply this by anything.
Yeah, you don't need to, it's just an extra step, just because people understand degrees more than radians.
That's
you
why I
know?
was asking the opposite, because I was just confused. You have to mess with it.
No, there's no need, just make sure you write your units in terms of radians or degrees accordingly.
Mike's already done. He actually did it within PE exam time, so. We got an engineer in the making. You sure you don't want to be an engineer?
It's in the past.
It's in the past. So sad.
I would only do structural.
You would only do structural?
Because it's to do with buildings.
Yeah. This is structural engineering.
Bridges are cool and all, but it gets a little repetitive. I feel like.
Buildings get a little repetitive too. You know what gets really repetitive? Tunnels. That's why I like it.
It's all the same thing.
Yeah.
Like with bridges.
Well, I guess it's not repetitive because there's bore drilled, there's blast and excavation, direct excavation, there's cover tunnels, submerged tunnels like the Queen's Channel, I think.
Yeah. Bridges are cool, but I did research into it and it's like,
You know, for that big Hampton Roads Bridge Tunnel project I was working on, it was initially supposed to be a bridge, but because of the high military presence over there, that's actually the military base my brother was supposed to go to before, you know, he was like, yeah, I don't want to go to Virginia. What?
it's by the beach.
Virginia Beach, yeah. Yeah, but because of the high military presence, they couldn't do a bridge because it was too much of a military risk or national security risk. So it's a tunnel.
The tunnel costs a lot more, right?
Yeah. The tunnel itself is probably about half the cost of the project.
And what's the other cost?
The approach structure, because it's not just necessarily the tunnel, it's the entire island that they have to expand upon to build the tunnel. So it's a big thing. That's an entirely man-made island too.
So do they just take what you dig from the tunnel and put it on the island?
Yeah, plus they have to export a bunch of the, or import a bunch of soil. So. Well, you're on the right track, everyone else. John, did you get it done?
We got the
Awesome.
same answers. That means something.
First of all, work is in,
Did you convert it to
Yes.
Did you try?
not
Did you
in
did it? Small.
It's only keeping room in, so keeping
one time.
unless it's like already 8 degrees.
Yeah.
then you-
Yeah. Well, good. Yeah, just the rotations. That would be an example problem on your. Yeah, so if you were able to do that in 10 minutes, right, that question will be a breeze on the exam. If you had struggles with it, you will have struggles on the exam. All right. You know what's ironic is every single question that I'm giving you guys so far is more complicated than any of the questions on the exam. So if you could do everything without any issues, you're probably going to get 100 on the exam. All right. So what we need to do is determine the angle of rotation in A, B, C, D, and FE. So what do we do first? We got to calculate what the force transfer is between these two faces here. So we're going to have some force transfer. That's still going the wrong way. This F is going to be consistent for both. Fortunately, because this and this are both 1 inch, so because of symmetry, the force transfer is the same. So for the force, it's just going to be 2 kip inches times basically the ratio of 1 inch to 2 inch. You would get that from the torque is equal to force times perpendicular distance. So what you get is basically a force transfer of 1 kip inch. Let me actually write out the full steps just to kind of prevent confusion. So 2 kip inches times, divided by 2 inches, I should say. Divided by 2 inches is equal to 1 kip. And then from there, the torque in FE would just be 1 kip times 1 inch, which gives us 1 kip inch. This is conveniently the same for AB. And then the torque, obviously, for CD is 2 kip inches, because that torque is literally just being applied directly on the rod. From there, it's as simple as just plugging in TL over GJ. So for AB, it's 1 kip inch times the length of AB, which is 6 inches, divided by 4,000 KSI, times 1 inch to the 4th. And this gave us, what, 0.0015 radians? For CD, CD has an internal torque of 2 kip inches. Multiply that by 8 inches. Divided again by 4,000 KSI times 1 inch to the 4th. And what did we get for that one?
We got 0.004.
And then for FE is the last one. 1 kip inch times length of 4 inches divided by 4,000 KSI times 1 inch to the 4th. And what do we get for that?
0.001.
All right, and then if you wanted to display your units in degrees, multiply it by 180 divided by pi, and that's your rotations in degrees. Did everyone understand this? Awesome. I amped up that problem slightly now. So I give you guys a rotation, and I'm asking you guys to find the shear stress within each of the rods. This one is a fun one, I think. Should challenge you a bit more. It's not as simple as plug and chug. Yeah.
Is that diameter or angle of twist for this 0.5?
At D,
Yeah.
that's the rotation at that point, so it's the angle of twist. Oh, let me freeze the screen. do example 3. Yeah.
The G's are different in this one.
Exactly.
So would the forces also be different? Or would they say the same?
Are the forces different? The What do you mean? The force that's being transferred through the gears?
Like like T, for example.
The torques should be the same, but well, you would need to work out the math. I think the torque for AB and EF are the same, but for CD it's going to be different. Okay. You guys are going to hate me for the next problem. Yeah. Yeah, where do you get that the rotation there? Yeah, how do you get that the rotations are all the same? I'm only calling out the rotation at one point.
So you have to find the filters for each one. Lines?
Yeah. Yeah, you do. Yeah. Yeah, this one's a fun problem, isn't it? Yeah. Oh, you're on the right track. 0.5 Yeah, so here's the thing. When it comes to some, it would be designed entirely separately. The rods that I'm calling out are these lines here.
So that's what those blue lines. Okay.
Yeah, that's what these diameters are.
Okay. Thank you.
Yeah, whenever you see like this, don't ever calculate J. They're do not.
The same
You did the same thing?
That's why
Figure it out yet?
I know it's not right, but
You know that's not right? 4,000 KSI. Let's see. Is equal to TL over DJ. So we want to calculate what the internal torque is, which would give you TGJ B
you have to come.
First issue, you're using degrees. That value is going to be divided by like 57 now.
So 0.5. I just don't know what's on it too.
Yeah, and that should give you the stress.
That makes sense.
Be careful with that. Your intuition was right. This lower value seems very large.
Well, I got this, so that makes sense then. Because I just got this value.
Okay.
So that's matching up.
That's aligning then?
Yeah, because
All right.
it's the same numbers.
Figure it out.
This kind of question you always ask. Yes, yeah. Ruby Castle,
Did you get it?
Ford,
I'm almost there.
I got it. I don't know if that's right.
but
Yeah. I'm almost there. You got all the shears?
Yeah, I just don't know if it's right.
Alright, I'll let you know when I get there.
it will be
Thank you.
Huh?
Cookie math. Math is math, and it's just kind of it's right.
Or is this just like a part of your problem?
I think you're overcomplicating. So the way that I would start off this problem is first off calculate what torque would cause that angle. Right, you get the torque,
Oh, yeah.
which then from there you can just use proportioning, which is what we've been doing, to then find everything else. So what you look like you did, can I see you back to what you were just doing? So 4,000 radius
That's right, like I said.
for
I first found the angle of the
CD,
for every single one.
1 inch, so your
And my
radius
angle
should be
was CD matched
5.
He gave me, so
Because
that's how I
CD
figured it.
Yeah.
So for
Rock rotation, it's 1 inch diameter. For this.
That's
I just said, do not do it for this.
Once to find the force.
But then I got
What the heck?
Because that's what I'm gonna do when we do this.
So
I got that force. and
4,000
do-
times 0.5
I got this one.
times. This looks right.
Okay, alright, I'll let you know.
I took the radius.
Yeah, so the radius is 0.5. For CD, it's 1 inch, so it would be 0.5 for the radius.
So.
Which gives you the shear stress here. The only thing that you need to do is just convert that shear stress to a torque, and then you can find the equivalent torques in these rods here, instead of just using shear stress.
So are these radius correct? Yeah, they are. 'Cause I just took.
Those J values,
But I completely disregarded the radius element.
this looks right. Calculating this shear stress is right, but with AB and FE, the angle of twists are not gonna be this. They're gonna be different.
So we need to find an angle twist.
Yeah.
Plug that in. Everything else looks.
Exactly, which the way you do that is by finding the torque in the work. Alright? You guys can take a break if you want. I was expecting you guys to be done like 20 minutes ago.
Wait, can you put what, can you explain it to me?
Explain it to you now.
So this is what I did. Find the torque in the CD.
Yeah.
Right now, and I have times that.
That looks right.
Okay. Now, now I have to find the angle torque for the other ones.
You need to find the torque in the other ones. The only way that you can really do calculations to find the stresses and angle of twist is by finding what force gets transferred through the gears, which requires you to know the torque in this rod here. We'll go over it at 7:30 if you guys end up getting. But now I know what type of question to add to the exam. I gotta make it more difficult. Yeah, because I'm realizing I'm over preparing you guys. So now I have to bump up the levels since everyone's gonna be too prepared.
You have to find J.
Say that again?
You gotta solve for J. And do an angle to
You have to solve for tau. Find the shear stress in each rod. Each rod is solid. Yeah.
For sure, I don't know. I can
No, I don't know either. I could be wrong too. So hold on, let me read through it and I'll see if I can.
Okay.
No, so you found the force. That's what this is. So the 0.038. Oh, but then yeah, that's the torques.
Okay.
So those are the torques. The only thing you need to do now is just tau is equal to T R over J. Tau is equal to T.
Yes, that's
And
what
then that's the
at the
problem.
very beginning.
And then since you already have the torque here, you can do the same thing.
Oh, that's the torque. That's the torque.
Yeah.
I already did that. I did that.
What did you do?
Somebody's got it. It's looking fine.
It should be.
A little bit suspect how you're doing that. I don't know what that is, but
Well, I found the torque here. So then
so the 0.009 is 5 times pi divided by 8, okay? So then 0.009 4,000 is 0.943. And then the J for CD is pi over 2 times.
it's point.
So then, yeah, that would be what, 4. Then, I think I'm just getting thrown because I've been seeing 2, but I think that's a shear stress, not the torque. So that looks right. 441 divide. This is trying to find the force, right? So this is
So let me continue.
So the thing is, for defining the force, you would find where the perpendicular distances go, which in this case is going to be that radius here, not the radius of the rod, because the forces are being transferred through the gears. So the gears only ever transfer forces, you won't ever see the rods transferring forces. So because of that, this should really be like 2 radius.
Okay.
And that's basically the force that gets transferred.
With force, one is I use the radius of this here.
No, this point is 75. It looks like you're using the radius of rod AB like you're using the radius here. But the thing is, there's this entire gear here that's transferring forces. So,
Okay, alright.
Get it, Michael?
let's see. Well, you're calculating angle of twist, which is sus. Because I asked you guys to find the shear stress. Oh wait, that's shear stress, that's shear stress. Sorry, I thought I misread it.
Hold on, because the teacher had to do this first.
How do you get 1 and 1 for the torques? For the
So you have to recalculate it.
Incorrect. Yeah, you need to calculate the torque. This is an entirely separate problem. All right, separate loading conditions.
Are we supposed to convert the degree of the 0.5 to?
Whenever you're using it in some type of calculation, the rotation should be in radians.
Okay, because we.
Yeah, the degrees, that's only ever for like displaying for like as a final result or to a contractor, or it'll be given to you in a problem statement. But other than that, always do the calculations with this in radians. Yeah.
Okay, so I just, wait, that's what I wanted to say, so that, what I was doing here, done up here, it should be 1, 2, 1, 3. So this is what it has in for, so
Yeah.
I can identify by this radius to get that force.
But the issue with this is the radius you're saying is 0.375. But that's the radius of the rod attached to the gear, not the radius of the gear itself.
I thought that was the radius given for the gear.
No, it's for the rod. Rod AB is 3/4 of an inch, but the gear itself you can see is 1 inch.
Oh, okay.
You see that?
Okay.
The lines don't do the geometry justice.
Okay.
On an exam, you'll actually have a better idea of how to
Okay.
figure lines.
Thank you.
Wait, how did you find your torque?
Huh? Remember the torque? So I used that, using the circle, angle of twist.
Yes.
And I did
The force is transmitted
CD.
through the gears.
And then I did.
And then the gears
G
basically
times the J over
transfer the
CD
force
that I
then
found,
directly to the
divided
rods.
by that length for the
The
torque.
torque for AE
And
and
then
EF
from
are
there,
the same
I'm going to
because of
find
that
these
fact that
torques,
they're geometrically the
and then
same.
I'm gonna find the shear stress as well.
Yeah.
He said 7:30.
Figure it out.
Well, I'm totally wrong.
I thought I was quick for a second, but thank you.
Yeah, they're in line
So,
with inches.
well, kind of.
12 kips per square inch, so they're pretty small shear stress. Alright, I've deliberately been choosing small shear stresses, just so that way, within a design setting, they're adequate. Plus you gotta remember, you're dealing with actually like relatively large, diameter rods in comparison to the force, so it's,
So wait, you did GR angle twist.
The angle of twist to find the torque from CD.
lot
Yeah,
of
I
Figure
did.
it out.
I did angle twist times G
I assume
times
so.
J equal L. Find the torque using that equation. We just did it on the first
Exactly.
question.
Yeah.
It's that one right there. If you want to write it on good. It looks great. Yeah, on the torque.
Did you hear angle twist?
I didn't find any.
Did it?
Using the first. I just wanted to use it.
Or you just use it as like a.
Because if you just use the first one, and then you just keep using the words, you don't have to find any of them.
Yeah.
I'll have a question.
All right.
Emily, did you figure it out? No? How far did you get that?
I erased,
You erased everything?
well, I knew it wasn't mine.
Before they get to Jake first.
Not quite.
So
For
we should
CD,
erase
you
it.
should get a right value for this, but the issue is, in this assumption,
For
for
the
ED
shear stress?
and FE,
No,
you're
just-
saying
yeah,
that the
just
angle of
for the
twist is the same, which isn't true. You would need to find the force that gets transferred, and then recalculate what the angle of twist is.
For the shear
Alright.
stress, I got 14.
No, what'd you get for the torque for 80?
For the torque.
You guys want to go over it or a few more minutes?
Does this look?
Almost done? Alright, I'll wait.
Does this look?
Absolutely not. I didn't even.
So I found this one, then that's what I get when I transfer it, because it's one, this other one.
Yeah.
Where'd you get that? I don't know, I'm gonna ask if it's right.
Because I got a different number. I got
It's
0.17.
right, we'll have to work out the numbers. Only thing though is, careful with the
You did
units. You're saying shear
0.008
stress
times
is in
4,000
units, yes, it should be.
times y over 2 to 0.375
Alright.
divided by 6.
Say?
Your procedure looks right, we'll see if the numbers are right.
Yeah.
Just because I don't know what the numbers are off the top of my head. Did you raise your hand or no? Who raised their hand over here?
Oh, I did.
You did.
Because I just wanted to see if this procedure was right.
Alright, you
Because I used that.
Well, this is the torque in CD. What is this radius here for gear C?
So that should be 2. But then once I do that, that should be fine.
Then you would multiply this by 1 inch, which would give you the shear stress. What is this value that you're dealing with?
Which one?
This is 0.441. Oh, this is TR over J.
Yes. Yeah, but I have to redo that. 'cause I
Yeah,
did
so
2.
0.441, and you're also using 0.031 for 80, but the issue is the rotations applied to CD.
So this would all just be CD instead? Okay.
Be careful with that.
But then AB and FE should be the same.
Not quite, because this is 6
Well, because
inches and
it's
that's 4
different.
inches. Yeah. Oh, I'm kidding. I have no idea. Your procedure looked right though.
Yeah, it's probably gonna have
What did you get? You got 6? Okay. Alright. Where did you get up to?
I erased it, I'm ready to start.
You erased it. Alright. Let's see. Need to unfreeze this screen. Yeah, that's 24 minutes over what I need to do it for. So.
Did we get it done in 24 minutes?
What?
Did we do it in 24 minutes? Or
No, you're 24 minutes over.
So it was like 34 minutes?
No, you needed to solve it in like. Oh, well, I gave you guys 10 minutes to solve it, right?
Yeah.
Yeah. All right. So I'm going to just shift. Yeah. So what we first needed to do was we needed to find whatever torque is acting in CD. So just ignore this right now. I am just going to drag that way down. So first, we need to calculate the torque CD, which you could use phi GJ over L. So this phi we said was 0.05 degrees. Oh wait, 0.5 degrees, sorry. Multiply it by pi over 180 to convert it to radians. The G was 4,000 KSI. We need J's for each of these, so we have JAB, JCD, JEF. For AB, you should have gotten oops, my pen turned off, 0.0311 inches to the fourth. Then 0.0982 inches to the fourth for CD. And then 0.0 6.1 inches to the fourth for EF. So for CD, we need to use the J value for CD, which is 0.0982 inches to the fourth, divided by the length, 8 inches. And this should give us a torque of around 0.428 kip inches. From here, we could calculate the shear stress directly within the torque using TR over J, or you could have used another equation. It's probably, I don't know it off the top of my head, so I'm just gonna go with this one. So you plugged in the 0.428 kip inches. The radius of rod CD is 1 inch, so the radius is 0.5 inches divided by the J, which is 0.0982 inches to the fourth. And you should have gotten a shear stress of around 2.182 KSI. Did everyone get that so far? Yes.
Convert the degree to that.
You have to convert it to radians. What? Oh. I threw the conversion right in there. Yeah. From there, we need to know what the torques in EF and AB are. The only way we can do this is by finding the force that's transmitted through the gears. So again, there's going to be a force being transmitted through each of these gears. And that force we can calculate as F is equal to the applied torque of 0.428 kip inches. And then you got to divide it by the radius of the gear, 2 inches. This should give us a force of 0.214 kips. And then from there we can calculate torque AB, which is conveniently also torque EF, because of the fact that the gears have the same radius. And this is just going to equal to 0.214 kips times 1 inch, which conveniently gives us 0.214 kip inches. From there, you could calculate tau AB using TR over J. So 0.214 kip inches times the radius of rod AB, which is going to be 3/8 of an inch, because the rod AB is a 3/4 inch diameter, so radius is 3/8, divided by that 0.0311 inches to the fourth. And what we should get is a shear stress of 2.583 KSI. And then I'm just moving this down. Then the torque EF is just calculated using the same equation. TR over J is equal to 0.214 kip inches. The radius of rod EF is a 1/2 inch, so you multiply it by a 1/4 inch. And then the J is 0.0061 inches to the 4th. Which should give us a shear stress of around 8.770 KSI. So this is CD, AB, and EF. Everyone got those answers, hopefully? All right. Now, since it's kind of late, I'm not going to give you guys a break. I'm kidding. I'll give everybody about 5 minutes. I know we're kind of late, so I'll let everybody's brains rest. But if you guys want to keep going, here's another example. It's a design one this time. Let me zoom in on this one. figure it out?
No, I just don't know what the first.
You don't know what the first step would be? What's given?
So,
Well, there's a force. Where's it located?
on E.
Well, it's not on E, but it's on here E. Towards one, along like one of the teeth, right? So what would that tell you? Based off of its location. You don't know? Ah, come on. Let's see. The answer's right here.
So, yeah, one of these, so would it be this one?
You tell me. Usually your first instinct is usually what you should do. At least when it comes to problems like these. If your first instinct is to jump off a cliff, don't do that.
I didn't get one of the flashcards.
I didn't give out flashcards, so I don't know. I did?
Like 2 weeks ago.
Really? Did you get? I did. Oh. Let's see. Did somebody move my flashcards? No. There you go. Christian, did you get a flashcard?
Yes. Thank you.
Did you two get a flashcard?
Yeah.
You did. Awesome. Next semester, the engineering students are going to get a pre-made formula sheet that I took from my professor at Stony Brook.
You're not gonna have them rated anymore?
No.
Why not?
Because engineering students are creative. What they would do is they would probably rip this in half, just like this, tape this, and then twist it in some way. Is there tape over here? Let's see. Maybe in here. No. There's a paper clip though. Nice. So they would do that. So they would formulate a shape like this, and that's a one-sided shape.
Oh.
I don't know if you see it. It's hard to tell, but if you trace your finger all the way around, it's one shape.
So then you use all sides.
They could use both sides while still having the one-sided flashcard. And then they would try and attempt to tell me, yeah, you told us one-sided flashcard. It means one-sided flashcard. I will not be letting you guys do that.
I feel like we wouldn't even need both sides for this one, huh?
For the engineering students, yeah, they will.
Yeah, that's probably.
Yeah. Edgar, did you raise your hand? No?
No.
Who did? Somebody raise their hand, or am I losing it? I'm losing it?
No, I'm raising it now.
Nobody? Oh, wait. What did you say?
I'm raising it now.
You're raising it now.
So it'll be the first.
Zach? And you can figure out everything else. Exactly. It took me 2 seconds to solve this, by the way. forgot to mention. Round to the nearest 32nd of an inch. I assume nobody's designed it yet, so I could just add that little detail real quick. Yeah, so this is like a very high tolerance lab that can manufacture stuff to this level. Construction, 16th of an inch is fine. Sometimes half an inch, quarter inch.
I'm not either.
Well, let me see. So
It's not,
we calculated the torque.
is that equal?
That is the torque. That's the torque at E. Alright. Now, what I would first try and do is find the torque in every single rod. Right, so you found the torque in at point E. What would the torque at C?
So now I do the opposite. Then you. That one?
So if it's 2,000 pound inches, you could divide that by 2. So what does that mean that the force trans? Well, if you divide it by 1, that gives you a 2,000 pound force transfer.
So it's 2,000. Yeah.
Yeah.
Okay.
So it's 2,000 pounds located there.
No, I mean this way. Okay.
Yeah. Which then you can find the torque at point C, and then you repeat the process and find the torque at A.
Okay.
Make sense?
Yeah.
Awesome. Last problem. What? Well, now I'm expecting you guys to solve it fast. I solved it in 30 seconds.
30 seconds.
Yeah. Just with the calculator.
It takes me 30 seconds to write it down.
You know, I was able to figure everything out. It's actually really easy. You just have to use a little bit of engineering judgment, and you can actually eliminate a lot of the steps. Go over it in 10 minutes. And then right before you guys leave, I'll show you guys the solution. It shouldn't take me any more than 5 minutes.
So wait, what is it that we're trying to basically find?
You have to design the rod. But the thing is, all the rods are the same diameter, which means basically find the worst case and design it.
So that would be deformation, right?
What?
We use a deformation for that?
Well, it has to satisfy both deformation and strength. So if deformation is satisfied but strength fails, then you know to use the strength equation. That's why you need to check both. I meant to do that. And then you guys got flashcards too, right? You and Olivia? Awesome. Everyone's got a flashcard. Yeah, I hope Professor Dawson doesn't miss these. I stole them from him.
Never bought them.
What?
Never bought them.
I wonder if the thing comes back. Yes.
you're asking how to do it now? Or no?
Yeah, kind of out of like, because I feel like that's confusing.
Okay, so you would divide both sides by the pi over 2. So the 0.109 and this. So that way you isolate the r. And then you would take power to, then you would just basically fourth root it, which is basically the same as saying square root of a square root. Or, an easy way of doing it, I believe, is on here. Oh. You can do it like that. So this value would be 4. Yeah, so then if I did it, so you would just punch in this number first, second, y to the x, and then get it forward. Yeah. Yes.
Find the total E now, just need 2 times the 5. This is the, because we don't have J, it's just.
You're finding J,
Right.
but that's
But don't you need?
that 4 inches is not R though.
I mean the 1 inches.
Oh, yeah, that gives you the torque there.
So then I would need, for E, we just need 2,000. So then to find CD, you just do like a.
You would have to use the proportion
F
again.
equals 2 over R.
Mm-hmm.
Okay. That makes sense.
Got it? Awesome. Figure it out? Not yet. Absolutely not. I don't know where you're getting with these. Wait, hold on. T. So where's J?
Yeah, that's what I'm confused on.
Okay, so you're using the deformation equation to find the diameter. That's okay. So what you basically need, you're given feet because you know that the deformation limit is 3 degrees maximum. So that's your known. And then from there, you can just size out whatever the radius will be for J. You could find what J is, knowing that the max radiation can be 3 degrees. Yeah. Got it? Thanks. How are you doing over here? Got it all solved, let's see.
J for your.
How do you get to Pascal? What about the torque in? Torque in is 2,000,
Yeah.
yeah. What about the torque in?
So,
Is it 2,000?
Yeah, so you just place J.
So value is not,
Yeah, so you do J equals T
divided by
3 times.
because I got that one,
Well,
but this one's
of course,
2,000.
E
And then
would be
divided
the
by
2,000
1.
pound inches
I thought you
divided by the
divided
1 inch. So your force is being transmitted through here is 2,000 pounds.
Yeah.
And then the torque at C would be 2,000 pounds times 2 inches. So the actual
Is
torque
that,
at C
are you
is
supposed to
4,000
divide by the
pounds.
radius of? Also,
Your
that's what
mistake
you're
is
supposed
going
No,
here
you're.
because you're saying 2,000 pounds, but then you're dividing it by 2 inches, even though the force here, this step, you should really be doing for everything in E. Does that make sense?
I'm gonna keep it.
Yeah, no,
though.
Yeah, no, but just keep in mind.
I know, everything's going so smooth.
Everything was going so smooth.
Yeah. Yep, that's engineering judgment. You knew something was wrong,
So
right?
you did,
Yeah, I was like-
2000
What was the diameter you were getting?
2,000
Like
divided
8
by
inches or
1,
something?
and multiplied by 2. But you could just skip that, 'cause it's just.
basically you find out what your radius is, and then you increase that radius to whatever 32nd of an inch it is. So for example, if you got a decimal value of like 0.0475, what would you round it to? Half inch, right? Because no contractor wants to be making something that's 0.475 inches. They want to make it to half an inch because it's the standard size. So in this case, round it to whatever 32nd of an inch, give you a nice round number, all right? Should be erasing everything for. Oh man. Yes, Thomas. Okay.
So. This
Yeah.
what's the units?
Inches to the fourth, as long as you did everything right. Alright. And since there's what?
I did it for, that's what he told us, trying to find it, so I was doing this, using the 3 degree max. The 3 degree max, I was using that as the AB twist, though, to find
No,
that.
it's not.
Because then that's gonna give it to you. Wouldn't you just have to design it as the previous? Because if you're on. Well, I'm using this to point to.
Generally, yeah. In this case, ironically, the one with the greatest work also has the longest lane. Otherwise, if the geometry was a little bit more ambiguous, like if this one was shorter, then you may have to check this one since it's the longest length for service.
Yeah.
Does that make sense?
Yeah, but since it's the greatest.
It has both the greatest length and the greatest torque. So
There's no-
really, the only thing I'm asking you guys is solve CD. So if you spent your time designing for EF and AV, you just wasted about all of your time. All right, let's go over it. Just because there's about 5 minutes left, and I'm sure you guys want this as a solution. So, torque, we need to design the rod. So, we specified that the rod was made from cold yellow brass or cold rolled yellow brass. The properties for cold rolled yellow brass include a maximum shear stress of around 36 KSI and a shear modulus of around 5,600 KSI. One thing to note is for this design problem, I didn't give you guys a factor of safety, so just ignore any type of safety factor contribution to it. If I gave you guys a factor of safety, you guys would obviously multiply the load by the factor of safety and design for that. In this case, you're basically like saying factor of safety is 1. So you're designing it as close to failure as possible. Not good, but whatever. All right. So what we need to do first is find the torques TE. So the torque in TE, which is conveniently also the torque at A, is going to be 2,000 pounds times the 1 inch perpendicular distance, which gives us 2,000 pound inches, which we can convert to 2,000 kip inches. From there, we need to find the force that's transferred. Ironically enough, this force here is going to be consistent throughout. So that force, no matter where you place your arm, is going to be the same no matter what. So if the gear was here and here, that force is the same through all of the rods. So the force that's being transferred, it's 2,000 pounds, which means that the torque at C is 2 kips times 2 inches, which gives you 4 kip inches. From there, we can design for one of 2 things starting off. What do you guys want to do? Serviceability, check the 3 degrees max limitation, or you want to check the 36 kips per square inch strength requirement? What do you guys want to do? Check strength or check service? You want to design for strength? All right, so we'll start off with strength.
And then I'll put can start with service though. And strength tells us that tau is equal to TR over J, which means that the 36 kips per square inch is equal to 2 kip inches times the radius of 2 inches. Nope, hold on, I'm losing my mind. Divided by R, I don't know why I said 2 inches, divided by pi over 2 R to the 4th. Now, we've done this problem enough to where for a solid section, for a solid rod, we can calculate R to equal the cube root of 2t over pi tau, right? This is just one of the equations that we have just consistently done from this equation here. And from this, when you plug in your values, 2 times the torque of 4 kip inches. Well, bleh, I keep on messing this up. So the question becomes, what is the torque? All right, how do we know which rod is the critical rod? Well, I'll tell you. The critical rod is going to be CD. And the reason for that is because it is the longest rod, which means it's going to have the most deformation, assuming that all of the rods are the same diameter, right? So the longest rod is going to have the most rotation. And then it also has the largest torque, because the torque at C is 4 kip inches, whereas the torque everywhere else is just 2 kip inches, right? So for rod CD, so I'll write a note here. Rod CD governs because length longest and torque largest. So we take the 4 kip inches divided by pi times 36 KSI, and what we should get is a radius of 0.414 inches. So, what would that be to the nearest 32nd? Did anyone even come up with a design for it? No? So I'm going to change this then just to be 1/16 of an inch because it's late and I do not think you guys want to be here waiting for me to figure out the nearest 32nd of an inch. So nearest 32nd of an inch is going to be 0.5 minus, what is it going to be? I get 7/16. 7/16 of an inch equals 0.4375 inches. All right. Now we need to check the rotation of rod CD using TL over GJ. So 4 kip inches. This should be a 4 up here. And then I'm just going to reorganize some of this just because you guys might get a little confused. So 4 kip inches, the length is 8 inches, divided by 5,600 KSI, times J, which is going to be pi over 2, times 7 over 16 to the power of 4. So 4 times 8 divided by 5,600 times shift pi over 2 times 7 over, is it 7/16? Yeah, 7/16 to the power of 4. And this gives us a rotation of, you guessed it, 5.69 degrees. That's when you multiply it by the 180 divided by pi. Is that within the 3 degree limit? No. Doesn't work. Which means redesign it for the rotation. So phi is equal to TL over GJ. We can rewrite this to say J is equal to TL over G phi, which is equal to 4 kip inches times the length of 8 inches divided by 5,600 KSI times 3 degrees times pi over 180 for the conversion. What we should get is a J value of 0.1091 inches to the fourth, which then, that J of 0.1091 inches to the fourth equals pi over 2 times R to the fourth. And so R is just going to equal the fourth root of 2J over pi. That's what it equates to. 2 times 0.1091 divided by pi. Which gives us a radius of 0.513 inches. Which means that when you round 0.5 to the nearest 16th of an inch, we should use a 9 16th inch rod. This is 0.5625 inches. And that's that. Sometimes serviceability will govern like it did here. Sometimes strength will govern. You know, you need to check both. Sound good? All right. If you guys have any questions between now and the exam, let me know. Shoot me an email. Otherwise, good luck with studying.